Welcome to our channel. Today, we discuss one of the most mind-bending mysteries in modern cosmology: why the universe is expanding faster than we thought. For decades, scientists believed they had a handle on how quickly the cosmos is growing, until new discoveries turned that understanding upside down. This isn't just a tweak to the textbooks. It's a cosmic puzzle that could rewrite the laws of physics as we know them. So grab a coffee, settle in, and let's unravel this astronomical enigma together. Our story begins in the 1920s with Edwin Hubble, the astronomer who first discovered that the universe is expanding. By observing distant galaxies, Hubble noticed something strange. The light from these galaxies was stretched into longer wavelengths, a phenomenon called redshift. The farther away a galaxy was, the more its light redshifted. This meant the universe wasn't static. It was stretching like a balloon being inflated. Hubble's discovery revolutionized cosmology, but it also sparked a question that still haunts scientists today: how fast is this expansion happening? For years, astronomers tried to pin down the universe's expansion rate using a value called the Hubble constant. Think of it as the cosmic speedometer. But here's where things get tricky. Depending on how you measure it, using nearby stars, distant supernovae, or the afterglow of the Big Bang, you get different answers. Imagine driving a car where your GPS, speedometer, and roadside radar all give conflicting speeds. That's essentially the crisis cosmologists are facing. This mismatch is known as the Hubble tension, and it's throwing our understanding of the universe into chaos. Let's rewind. In the 1990s, astronomers made another groundbreaking discovery. Not only is the universe expanding, but that expansion is accelerating. This was like throwing gasoline on Hubble's balloon. The culprit? A mysterious force called dark energy, which makes up about 68% of the universe. Dark energy's push against gravity is causing galaxies to flee from one another faster and faster. But even after accounting for dark energy, the numbers still don't add up. When scientists use the cosmic microwave background, the faint glow left over from the Big Bang, to calculate the Hubble constant, they get a slower expansion rate than when they measure it using nearby stars and supernovae. The difference isn't small. It's like expecting a car to go 60 miles per hour, but clocking it at 70 miles per hour instead. So what's going on? Could our measurements be wrong? Let's dig into the methods. One approach uses Cepheid variable stars. Stars that pulse in brightness at rates tied to their true luminosity. By comparing their apparent brightness to their actual brightness, astronomers can calculate distances. Pair this with redshift data, and you get the Hubble constant. Another method relies on the cosmic microwave background, CMB, the baby photo of the universe taken 380,000 years after the Big Bang. Using the CMB, scientists extrapolate how the universe should have expanded over 13.8 billion years. But these two methods disagree by about 5 to 10%. That might sound minor, but in cosmology, even a 1% discrepancy can signal a fundamental flaw in our theories. Now, some scientists argue that the problem lies with measurement errors. Maybe Cepheid stars aren't perfect distance markers, or perhaps the CMB data is being misinterpreted. But after decades of cross-checking, the gap persists. This has led to wilder theories. Could dark energy be evolving over time, growing stronger or weaker? Or is there an undiscovered particle, like a dark radiation, giving the universe an extra push? Some even suggest our universe collided with a bubble of another universe, injecting energy that sped up expansion. But the most tantalizing possibility is that our laws of physics are incomplete. Einstein's theory of general relativity has been the backbone of cosmology for a century, but it might break down on cosmic scales. For example, what if gravity behaves differently over vast distances? Or what if dark energy isn't a constant force, but a field that changes dynamically? These ideas are speculative, but they're gaining traction. In 2023, the James Webb Space Telescope began delivering sharper data on Cepheid stars and supernovae, hoping to resolve the tension. Early results? The discrepancy hasn't budged. If anything, it's gotten worse. This isn't just academic. The universe's expansion rate affects everything from the fate of galaxies to the ultimate destiny of the cosmos. If the expansion is faster than predicted, galaxies will vanish over the cosmic horizon sooner, leaving future civilizations with a sky devoid of stars. It could also mean dark energy is more dominant than we realized, pulling the universe apart in a Big Rip scenario. Or perhaps we're missing a piece of the puzzle that connects quantum mechanics to gravity, a theory of everything. What's next? New telescopes, like the Vera Rubin Observatory and the European Space Agency's Euclid mission, are mapping the universe in unprecedented detail. They'll study dark energy's influence and measure the Hubble constant with fresh techniques. Meanwhile, physicists are revisiting exotic ideas, like modifying gravity or adding new particles to the standard model. The stakes are high. If the Hubble tension holds, it could mean a Nobel Prize for whoever cracks it, or an existential crisis for cosmology. So what does this mean for us? On a human scale, not much. But on a cosmic scale, it's a humbling reminder that the universe is far stranger than we imagine. Every time we think we've got it figured out, the cosmos throws us a curveball. And that's what makes science so thrilling. It's never done. If you enjoyed this cosmic deep dive, smash that like button and subscribe for more mind-expanding content. Drop a comment below. Do you think we'll solve the Hubble tension in your lifetime? Or is the universe determined to keep its secrets? Let's geek out together. Thanks for watching, and remember, the universe isn't just expanding, it's showing off.